Hey everyone, welcome. Today, we're not just learning math, we're actually building a powerful toolkit. We're going to assemble all the essential concepts you need to really master second-order linear differential equations, one tool at a time. So you ready? Let's open up the box and get started. What's so cool is that all these different things, the swing of a pendulum, the electricity in a circuit, the vibrations in a spring system, they can all be described by the exact same kind of equation. These aren't just abstract symbols on a page. This is literally the language of the physical world. And the key to unlocking it all? It's understanding their shared mathematical blueprint. Okay, so every great toolkit needs a solid foundation, right? So our first step is to really understand the fundamental blueprint for every single equation we're going to tackle. Think of this as the master plan that everything else is built on. And here it is. Now, I know at first glance it might look a little intimidating, but let's just break it down. The second order part, that just comes from the y double prime, the second derivative. Linear, that's just a way of saying that our variable y and its derivatives aren't being squared or multiplied together. The a, b, and c are our coefficients, and that g of x all the way on the right, that's our forcing function. We'll get to that in just a moment. So this right here is a really crucial distinction. When that g of x is 0, we call the equation homogeneous. You can think of it as the natural, undisturbed state of a system. But when g of x is not 0, it's non-homogeneous, which just means there's some kind of external force acting on the system. Now, to solve the more complex, non-homogeneous cases, you first have to get really good at the homogeneous blueprint. And that's exactly what we're going to focus on today. All right, let's add our first major tool to the kit, the superposition principle. This is an incredibly powerful idea. Basically, it says that if we find a few basic solutions, we can just combine them to create an infinite number of other solutions. It makes our job so much easier. And this sums it up perfectly. It's kind of like having two fundamental Lego bricks, y1 and y2. The superposition principle is the guarantee that any structure you build by combining them, like 3 of the first brick plus 5 of the second, is also a valid, stable structure, or in our case, a perfectly valid solution. So we know we can combine solutions. That's great. But how do we know we have the right solutions to combine in the first place? Well, that brings us to our next tool, which is basically a quality control check for our building blocks. And this is the whole point. We need solutions that are genuinely different from each other. So, for example, e to the x and 2e to the x, they're linearly dependent because one is just a multiple of the other. They're telling us the same basic thing. But something like e to the x and x squared, those are linearly independent. They represent fundamentally different behaviors, and it's by combining those that we can build a complete general solution. Right, that's the million-dollar question. You can't always tell just by looking at two functions if they're truly independent. We need a solid mathematical test, a definitive tool that gives us a clear yes or no. And that tool is called the Wronskian. It might look a little messy, but it's our official quality control test. All you do is take your two functions, f and g, find their derivatives, and plug them into this formula. And the rule is super simple. If the Wronskian is anything other than 0, your functions are linearly independent. They're good to go. Let's actually see it in action. So let's say we have two potential solutions. y1 is e to the 7x, and y2 is e to the 2x. First, we find their derivatives, which you can see right there in the table. Then we plug them into the Wronskian formula, y1 times y2 dash minus y2 times y1 dash. The result we get is negative 5e to the 9x. Now, since that expression can never, ever be 0, the Wronskian test confirms it for us. These two solutions are linearly independent. We are good to go.
All right, so we've got our blueprint and we've got our quality control check. Now it's time for the real power tool in our kit, a method that turns a tricky calculus problem into simple high school algebra. It's awesome.
This right here is the magic step. For equations where a, b, and c are just numbers, constant coefficients, we can create this thing called the characteristic equation. You just swap y double prime for r squared, y prime for r, and y for 1. And just like that, we're solving a basic quadratic equation. The roots of that equation are going to tell us everything we need to know. So the roots of that equation will always fall into one of just 3 categories. This table is your roadmap. If you get 2 different real roots, your solution is a mix of 2 exponentials. If you get 1 repeated real root, look closely. The second part of the solution just gets an extra x multiplied in. And then, if you get complex roots, something really beautiful happens. Your solution turns into an oscillating wave with sines and cosines. This one table is pretty much the key to solving a huge class of these problems. So, we've built a fantastic toolkit for second-order equations. But what about third order, fourth order, or even higher? Well, let's see how the tools we've already made can scale up to handle even bigger challenges. Okay, this might look a little scary. It's the general form for an nth order equation. But here's the good news. The fundamental logic doesn't change one bit. We're still going to form a characteristic equation. It'll just be a higher degree polynomial. We're going to find its roots, and those roots will build our solution. All the same principles we just learned still apply. And this shows you exactly how the rules scale up. Remember how a repeated root in a second-order problem got an extra x? Well, if a root is repeated 3 times, it generates 3 solutions. The base one multiplied by x, and another multiplied by x squared. It's a simple and elegant pattern that turns a really complex-looking problem into a straightforward process. And finally, every good toolkit has to come with a guarantee, right? In math, that guarantee is a theorem, and this one tells us when we can be absolutely confident in the solution we found. So let's check out the fine print. Here's the promise. As long as your equation meets a couple of reasonable conditions, the coefficients are continuous, and the leading one isn't 0, then for any set of initial conditions, there is exactly one solution. Not 2, not 0, just 1. This theorem gives us the confidence that when we find a solution, it is the solution. So we've done it. We've assembled a complete toolkit. The blueprint, the superposition principle, the Wronskian for quality control, the characteristic equation for actually solving, and the guarantee of uniqueness. With these tools, you literally have the power to model and understand a huge range of systems in physics, engineering, and beyond. The only question left is, what are you going to start with?